Good morning. I'm back. I watched Ari's lecture. It was terrific. I felt I learned a lot myself. But so I'm going to just pick up on some of the completing some of the material with filtered back projection, and then we'll move on to MRI. So, are there any questions or comments? I think it seemed like there were a few questions about due dates for laboratories and things, but they got resolved in the email, so I assume everything's clear. And if you have any questions, email Jordan. I think everybody has Jordan's email address, right? Jordan's very responsive. And so is everything good? Should I start? Okay, I'll start on the lecture material. So let me just actually back up a little bit more to review the algorithm. It's just to get you thinking about what was covered in the last lecture. So the convolution back projection algorithm basically has three steps. The first step is you measure the projections. And of course that depends upon the particular modality, but if it's CT, you just measure it by using taking the log of the photon count and using the relationship that we described. It's called Beer's law. And by taking the log, you get the line integral of the attenuation of the density. So that gives you the projections. That's a physical measurement. And then once you have those projections, then you filter the projections, and that with a filter H. And then once you filter the projections, then you do a back projection, this is the back projection. So the back projection is really just the adjoint or the transpose operation of projection. So it's kind of, you might think of it as like reversing it, but it's the reverse of projection, but it's not the inverse of projection. In the same sense that the transpose of a matrix is not typically its inverse, right? So if you have here's an example of one of my famous tangents, okay? So you have a matrix A, okay? So you multiply it by X and you get Y, okay? So this is a n by n matrix, right? So the transpose or adjoint of that matrix, adjoint is a little more general concept because transpose has a precise definition for a matrix, which is n by n, okay? But you can generalize the concept of linear operators to inputs that are infinite dimensional, like operators from functions to functions. So adjoint's a little more general. Okay, so but the adjoint or transpose of A is A transpose, right? So the transpose has the property that you take the input space to A transpose is the output space of A. So you're kind of so if you have this is the domain and this is the range, right? And then A is a mapping like this, and A transpose is a mapping back. But in general, A transpose is not equal to A inverse, right? When is A transpose equal to A inverse? Not just symmetric. No, symmetric isn't orthonormal, right? So if the transpose is the inverse, it means the matrix is orthonormal. And most matrices are, if you take an arbitrary matrix, it's a random matrix, you might say, it's not likely to be orthonormal. But it turns out that the transpose often shares a lot of properties, and sometimes can be used as it's sort of an approximation to the inverse, roughly speaking, okay? Or at least plays a role in inversion. So the back projection is the adjoint, or essentially the transpose of the projection operator. So it's not the inverse, but if you do the filtering before you apply it, it is the inverse, under the conditions that you take a full set of projections. So it's an interesting result. The result is derived. I think Ari went through that, so I won't.
'll go through the derivation, but I'll just kind of review.
go through the derivation, but I'll just kind of review. The result is derived. I think Ari went through that, so I won't go through the derivation, but I'll just kind of review. The result is derived. I think Ari went through that, so I won't go through the derivation, but I'll just kind of review what it means. This is the filter that comes out of the derivation, and the reason you have this filter, it depends on the absolute value of rho, because rho is like the radius in polar coordinates when you're taking the inverse transform. So essentially what is happening is you have a weighting by the magnitude of rho, because when you take integrals in polar coordinates, right, you know this from undergraduate or high school calculus, the size of the little slice increases, the volume of that, the area of that slice increases as r. So this distance here would be rho, and this distance is d theta, right? So the area of that little incremental slice is going to be proportional to rho. So that's where this term comes from. So when you you multiply the frequency domain by this. Well, that's the same thing as convolving in the space domain with the inverse Fourier transform. Now, this function really is supposed to go out to infinity, but if the image or the object you're doing the reconstruction of is band limited, then it doesn't need to go to infinity, because if the signal goes to 0, well, then you can clip the frequencies of the filter off also. So another way of thinking about it is that you're actually imposing band limiting on the reconstruction. So typically what you have to do is cut this off at some point, because otherwise you'd create, if you have the gain go to infinity, well, you're going to just create a lot of noise, basically. So you cut this off. So you can take the inverse Fourier transform of that, and that's easily done because this is like a rect function minus a triangle function, and the triangle function, which is the gamma function, the triangle function is formed by the time convolution of the pulse width itself. So you can calculate the Fourier transform of both. So the Fourier transform of the triangle function is going to be like a sinc squared, because when you convolve something in time, you multiply it in frequency, and the Fourier transform of the pulse is going to be a sinc. So the Fourier transform of all this is going to be something that looks like a sinc minus a sinc squared, but there's some scaling constants, because when you did the convolution of the pulse width itself, it should have gotten twice as wide. So you have to scale it. So you're actually scaling it in this way. So in time, you scale it out, okay, and that's kind of how it works. You can plot this function, and if I take the integral of h of r dr, what's that equal to from minus infinity to infinity? So when we get done this course, that's one of the things I insist that everyone learn. They should be able to know the answer to this question instantly. So h is the impulse response associated with this frequency response. So what's the integral of the area under the impulse response? By the way, just as a matter of reference for the future, whenever you don't have any idea what the answer to a question is, one possibility is that the answer can be 0, okay? Another possibility is the answer can be 1, okay? If those don't work, a good bet is 2 pi, okay? I don't know. What else? Those are. I would stick to those first, okay? So among the answers, which one do you think could be correct? 0, 1, or 2 pi? 1's a good guess. How many people go for 1? You're wrong. Sorry. It's 0. It's the Bayesian distribution on all answers to exam questions. So, okay, you get the answer to that question wrong once, okay? And from this point forward, you have to know the right answer. So, whenever you have, when you have the Fourier transform between two things, okay? So over here you have, say, h of f, okay? And h of f, is the Fourier transform of h of t. So this is the continuous time Fourier transform, right? This thing's not doing so well. Then if I ask, well, what's the integral of h of t dt from minus infinity to infinity? That's the area underneath the kernel, right? So what's the area underneath the kernel going to be? So how many electrical engineers are in the room? So you have a filter, right? And you have a signal going in, right? And it's x of t, right? And let's say that x of t is equal to constant c, okay? So you put what's the output going to be? If you put a constant input into a linear time invariant filter, what's the output going to be?
CHT.
What is it?
CHT.
C times what?
H.
Times h of t?
Sure. It's just a constant.
H naught.
If it was x of t, it would be x convoluted.
It's the convolution, right?
Right.
Okay, so it's a convolution. Okay, so I can write that down. So it's going to be y of t equals the integral of, well, it would be, well, I can either make it x of tau times h of t minus tau d tau, right? That's the convolution. And in this case, that's going to be equal to the integral from minus infinity to infinity of some constant times h of t minus tau d tau, right? Oops. And what's that equal to? Let me back up a little bit. Okay, this is a linear time invariant system, and it has frequency response to h of f and a time response of h of t, okay? And I put a signal in it which is x of t equals e to the j omega t. What's the output?
E to the j omega t convolved with h.
It's going to be e to the j omega t times what?
Convolved with h.
H. Involved with h, that's true, h of t, right?
Right.
But what else? I mean, there's a simpler form.
It gets multiplied with the h and the frequency, like h omega in frequency.
Times h of omega, right? That's what the frequency response is. The frequency response is the constant, the complex conjugate you multiply a sine wave by, because this is the amplitude and phase. That's why when you buy, well, I mean, maybe nobody does this anymore, but when you buy an audio amplifier, they plot the frequency response, right? Well, I don't know, does anybody know that they plot the frequency response? So it looks like, you know, something like this. So this is 20 hertz, say, and this is 20 kilohertz. And then hopefully it's kind of flat. So what does this function mean? Oh, this is h of... Oh, I switched into omega. Oh, I'm sorry. I spontaneously switched from f's to omegas. I do that accidentally, okay? So f is just... omega is equal to 2 pi f, okay? But, so this is going to be h of f, right? So if I put a frequency in here, so this is equal to 2, okay? So if I put a frequency in here with an amplitude of 1, what's the amplitude going to be on the output? 2. This is the gain, right? And of course, it's a complex number, so it has a phase also. So the frequency response of the system basically tells you what you multiply. If you put a sine wave in, it tells you what you multiply by, what happens to the gain and the phase of that sine wave when you put it in, right? I mean, that's what frequency response is. That's why you take the Fourier transform. Because when it was the Fourier transform converts convolution into multiplication. Instead of having the convolutive functions, you take the Fourier transform and you multiply them, right? So what ends up happening is that y of f, I got to catch myself, is going to be equal to x of f times h of f, right? So I mean this is sort of this is one of the most important equations in electrical engineering, perhaps more important than V equals IR, okay? Okay, so because it tells you that why people talk about frequency and hertz, okay? Now, what if I have a constant input, what's the frequency? 0. That's what they call, electrical engineers call DC, for direct current. Okay? So if you have a DC input, then what's the output going to be at DC?
CH0.
It's going to be C times H of 0. Right. That's what H of 0 is. It's the gain at DC. And H of 0 is always a real number if the impulse response is real, because the frequency response has to be conjugate symmetric. So at 0, that means that H of 0 has to equal H star of 0. So it has to be real value. Okay, so H of 0 tells you how much area is under the impulse response. Okay? So this is one of the things that everybody in this class has to learn, and if they don't know it, like, it's going to be bad on some exam, okay? That what's going to happen, that H of 0 is equal to the integral from minus infinity to infinity of H of t dt. It's the area under the curve. Put another way, I mean, just write the Fourier integral down. You know that H of f is equal to the integral from minus infinity to infinity of H of t times e to the minus j 2 pi ft. Is that correct? That's the formula for the transform, right? So in the case where f is 0, this is e to the 0. So in that case, this becomes just 1. So it's an easy way of proving it, but the intuition is absolutely clear, okay? Now, in 2D, that means that in the point spread function, if you have in image processing applications, you usually don't want the filter to make the image brighter or darker. You want that to stay the same. So if H of uv evaluated at u equals 0 and v equals 0, if that's equal to 1, that means that the integral over R2 of h of xy dx dy, that has to equal 1. So the area under the point spread function has to be 1. If the area under the point spread function is not 1, if the area under the point spread function is 2, what's going to happen after you filter the image with that point spread function? It's going to get brighter by how much? It's going to be twice. It's just going to have a gain of 2. So this should be hardwired in your brain, okay? Because that's an important. So if going back here, where we kind of took a little tangent, this filter has, if I compute the integral of this impulse response, what's the integral of the impulse response in this case? So what's the Fourier transform of h of r?
The function of h of r.
So what's the Fourier transform of h of r is what? H of rho, right? That by definition. These are Fourier transform pairs, right? So what's the integral of the area under h of r? It's going to be this h of 0, right? And what's h of 0? 0. So it was answer A, the most likely answer to any question. Okay. Although it'd be better if you actually know why it's true. But anyway, the 0. So you know that the impulse response of this filter has an integral of 0. You should be able to do those kinds of inductions, or you should be able to go back and forth and say quickly on that. Say, oh, okay, well, the filter's gain is 0 at DC. The area of this is 0, or if it's 1, this is 1. Usually in filters you apply to images, their gain is 1. So there's an interesting paradox here, which is that the gain of the filter at 0 is 0, but the reconstructions you get are all strictly positive. How's that possible? I'll let you ponder that, okay? It's sort of it's an amazing paradox of filtered back projection, but it's true. Okay, so you filter with this filter, each of the projections, and then you back project. And the back projection, I think Ari described you take the filtered projection and you slide it back over the image. And that just is the adjoint operation to the projection. It's the transpose operation. So in the forward projection, you add all these variables together. In the back projection, you take some value and you proportionately put it at each location in proportion to the additive weight you used to add it up in the first place. So they're transpose operations. The range becomes a domain, and the domain becomes a range. Okay. So now let's look at this. I have an example which you can look at. Actually, you can run the MATLAB code. So that's an object. It's actually two objects. Each object has a different density because this is a different color than that. The brighter objects are more dense. That's kind of the convention. 0 represents an absorption, a density of 0. So this is, this represents actually the density value, and the minimum value of the density is 0. Because you can't have a negative density, because that would mean that the material actually would amplify the energy. You would need like some kind of active amplification material for that to be. Any passive material, it can only absorb energy, so that the density has to be positive. The number of photons that come out has to be less than or equal to the number of photons that go in. So this is sort of the theoretical object. It's been discretized. So you can see it's pretty relatively coarse resolution. It's only 64 by 64. So then you take the projection. These are the projections. Now the projections are computed at different angles. Generally, you compute the projections between 0 and 180 degrees, because if you compute them beyond 180 degrees, then it just starts repeating. So let's say you're taking the projection this way. That's 0 degrees, right? And this is 45 degrees, okay? 90 degrees. That's 135 degrees. This is 180 degrees. So 180 degree projection and a 0 degree projection are the same thing. Because it doesn't matter which direction you integrate in. You still get the same integral. So once you go past 180 degrees, you really just start repeating. Now there's actually, in practice, some value to going beyond 180 degrees. Because, well, first of all, you get multiple measurements of the same thing. So you get higher signal-to-noise ratio. And then they also play some clever tricks, typically, which is that I'm assuming continuous measurement, but in practice it's never continuous. You have to discretize it. So you have detectors that are discrete and that sample it spatially. And what ends up happening is that if you're clever and you offset the detectors correctly, your measurement in this way will be just slightly different than your measurement that way. because the sampling will be offset. So you get staggered sampling, and that's helpful because when you stagger the sampling, you get more points in between. So in practice, they actually do scan more than 180 degrees because there's some benefit to it. But theoretically speaking, if you had a continuous perfect sampling, you wouldn't need any more than 180 degrees. And there's no noise. There would be nothing to be gained. Okay. Now when you at 0 degrees, hold on, how did this get done? Okay, 0 degrees according to this. So this is X and Y. Looking at this, it looks like the projection was done like this. So usually this is 0 degrees projection. Hold on. Oh, how do we do this? Oh, okay, 0 degrees. Okay, the way I did it in the book. Okay, there's more than one convention for this, but okay, I think 0 degrees I actually had set up this way. Okay, because because if you look how I have it set up, when theta is 0, then the projections are straight up and down. Because this angle here is theta, and the projections are like this. So if that theta is 0, then the projections are up and down. Okay, so if you took 0 degrees, you get the projections like this. So at 0 degrees, you're going to see two things, okay? This is going to be a little thicker than that. Now, that one is, this has greater density, but this is larger. So the integral of this density is likely to be larger than the integral of that density. I mean, I don't have actual values here, but just, this doesn't look like it's numerical. The numerical value is twice as large, and this is much more. This is maybe like, I don't know, 5-6 times longer. So when you actually, so this is the result here. So that function right there at the top is the projection, and sure enough, you have one bright projection, that's a large integral density, and one less bright, that's the smaller circular thing. So this is the oblong thing. Now, as you start tilting, the oblong thing starts looking wider, but it also starts looking less dense. So by the time you get to 90 degrees here, which would be halfway, the density of this small spherical thing stays the same. Now, it looks like it gets higher because you're integrating that density with you're passing through both objects. But the integral density of just a smaller object by itself remains constant because it's circular. But the other one gets spread out, so it's wider and less dense. And it comes back then. Now, so you notice that these make sort of sine wave patterns, and if you went 180 degrees, if you went 360 degrees, it would come back again. So they call this a sinogram because a single point has a trajectory along a sine wave. I like to think of it sometimes as, when you have a bicycle wheel like this, and you have the stem on the wheel where you fill it with, and if you're looking at it from, I don't know, is that what a person looks like? Not really, but if you're looking at it here, then you're seeing the projection of the wheel as it spins, right? So you hold it by the axle and you spin it, right? And it goes zzz, 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 and it looks like it's going up and down, and the pattern is a sine wave, and that's what you see here. Okay, so now. So now you take that sine. So this is the sinogram. Okay. Then you take the sinogram and you filter it with this filter. What's the integral of this filter?
0.25. 0.25.
No. So if you take this function, this is h of r, and you integrate it. I'll give you a hint. We just discussed it for quite a while.
Why not? Which way?
Someone answer me, please.
0.
0, thank you.
Why is it 0?
I don't know if you used my Bayesian surefire method here, but you gave me the right answer, so it made me happy, okay? But it's 0. Why?
I thought the point at 0, I thought, of the filter is what gives us the integration, the integral.
So this is the time domain signal.
Oh, okay. I'm sorry. I thought
Yes, this is the point. This is the filter's impulse response.
Gotcha.
Okay, so its integral is going to be 0 because it's that point right there. Okay. By the way, what's the integral of this thing going to be?
0.
The integral of the what's the integral of the frequency going to be? Now this is kind of a trick question. Duality tells you what.
Okay.
It's going to be
It's going to be h at time 0, right? I don't know what that means exactly, but it's true.
Right.
Okay. The other one has a lot more physical meaning. Okay. You very often want to know what the DC gain of a filter is. So to know the DC gain, by definition, it's the value of the Fourier transform at 0, which is the integral of the impulse response. So you'll know that from this point forth, right? So and it's reasonable to believe that the integral here is 0 because some of the filter is positive and some of the filter is negative, and they kind of look like they might cancel each other out, right? So you take this. Now, what do you do with this filter? Do you multiply them? Do you like tape them together? Do you go like this? I mean, what do you do with it? What is an engineer to do with a filter like this? Well, you take it and you filter the rows, okay? Because these are the projections at each angle. So you take a projection at a single angle and you filter it with this 1D function. Because this is a 2D function, right? This is a 1D function. You take this 1D function and you filter each row of this 2D function. Okay? And when you do that, this is going to sharpen the edges because this is high pass. So basically, you're going to you're going to accentuate the edges at these transitions, right? And that looks like this. See, because it accentuated the edges. Does that seem reasonable? Now what you're going to do is you're going to take for each function, for each projection angle, you're going to take that function and you're going to back project it. And you're going to add the back projections from each projection angle. So you're going to add the filtered back projections. That's why it's called the filtered back projection algorithm. So if you add the first filtered back projection, you get this. So that's just the filtered projection at angle 0 and it's smeared back over the image because that's what the back projection is. You smear it back over, okay? Does it look like the original image? Do those look the same? Well,
You could see where one might get it.
yes, you could see where one might. That's a kind way of putting it. They really look quite different, but it's a start, okay? And then what you do is you say, okay, well that wasn't so good, so I'll do another one. I'll back project not just at angle 0, but angle 90. And then I get this. Maybe it's a little closer. And then I do the 245s. So this is the back projection of 4 angles. And this is the back projection at 8 angles. The theory says that if I take an infinite number of back projections, filtered back projections, I'll get exactly a perfect reconstruction if the original signal was band limited. But the original signal isn't band limited, so I won't get perfect reconstruction. You'll get some smearing of the edges because you had to sample it. See, so that's 16. And this is, I assume this is probably 64 back projections. So it's a 64 by 64 image. You usually need to take, if you, you need to take enough projections that you're taking, that the rotations, as the resolution of the image goes up, you need to have more projection angles. Roughly speaking, the number of projection angles you need is, to reconstruct an n by n image is roughly n. You need to reconstruct an n by n image. You need roughly n, or maybe 2n projection angles. and then you need, as you might imagine would be reasonable, the sinogram needs to have about the same amount of information in it as the image you're trying to reconstruct. Otherwise, you'd be getting something for nothing. So, where's the sinogram? So in order to be able to reconstruct a 64 by 64 image from this data, you have about 64 projection displacements. You need about 64 projection angles. So the number of unknowns is equal to the number of measurements. So any questions about that then? And you can run the simulation on MATLAB.
Complexity becomes n cubed then.
Excuse me?
So the complexity of the runtime.
Oh, it's an interesting question. Yeah. So the matrix A. So let's say that you have an image, okay, which is n by n, okay, and then what we're going to see is to do this. You can think of it as the matrix A that you multiply by x. X here is an image. But we're going to represent it as a vector, which is of length n squared, because it has to have that many pixels in it. So then A here is an n squared by n squared matrix. So A gets to be really huge. But fortunately, most of the entries in A are 0, because what happens is that if you have an image, and you take and this is of some voxel, okay? And you take some sort of projection. Chances are the projection doesn't go through that voxel. So if this is voxel j and this is projection I, then the entry ij is going to be equal to the intersection of that voxel with the this is the intersection voxel j with ray I. So the intersection of voxel j with ray I is going to be is what aj is. So most rays don't intersect with most voxels. So most of the time these entries are 0. So this matrix is sparse. You say something sparse if most of its entries are 0. Sparsity is all the rage these days. Everybody loves sparsity. It used to be convexity. Everybody loved convexity. Then people kind of got tired and they abandoned. Poor convexity probably is feeling kind of lonely now. But so everybody loves sparsity. Okay, so this is great. So sparsity is good for lots of reasons. One reason it's good is because it reduces computation. So if you want to multiply x times a, if you have to do the full matrix vector multiplication, it would be a huge amount of computation, but you only have to add together the entries that are non-zero, so that makes it much faster. And there's a lot of support, even like in packages like MATLAB, for sparse matrix operations. Then, so the number of entries, if you look at it, the number of non-zero entries in this matrix are typically around n to the n cubed. Okay, so each voxel gets touched by all the projections that a projection at each angle, roughly speaking, and they're usually about n projections at n angles. So instead of being the n to the fourth, it's n cubed, the number of non-zero entries. So the forward projection is typically complexity n cubed. But there are algorithms to make it faster. Okay. Any other questions? But it's good thinking about complexity because when you implement algorithms, you have to have a sense that if you wait a half an hour, sometimes what will happen is a student will say, well, I wrote the program, it's been running for 2 days, so it should be done any time now. Okay? So, I mean, but if it's running for 2 days, who's to say it's not going to run for 4 days? And they say, well, it's been running for 4 days, and now I'm sure it has to be done. Okay? It might take 3 weeks or 6 months or a millennium. Okay? How do you know, right? Well, you have to have a rough idea of how much computation you're doing, how fast the computer is, and where you are. Okay? So it's a very important thing to have an understanding of. Okay, I'm going to talk about MR next. We'll just start this, I think. We don't have a huge amount of time left. Okay, MR is a very different modality than CT. Yeah, sure, they're both like white plexiglass donuts, but beyond that, it's quite different, okay? So, or not plexiglass, fiberglass. If they were plexiglass, it would be kind of weird. It would be like the Visible Man or something. Okay, so what MR has some advantages and disadvantages to CT. Because you'd say, well, why don't they just get rid of them and just do one instead of both? Well, they each have strengths and weaknesses, so neither can completely replace the other. Although there are some things that they can both do, and they compete for basically healthcare dollars. Okay, so the well, first of all, MR can be very well. CT is very high resolution, but MR can in principle be higher resolution because you can just there's no kind of limit. Or at least. The limits are, if you're willing to spend lots of time and scan very slowly, you can really increase the resolution a lot with MR. But it's a practical matter. The resolution is limited for the amount of time that people can be willing to spend and for the systems that are available. Okay, a big plus to MR is there's no exposure to ionizing radiation. It's just RF signals, which there's a little bit of controversy about. Okay, RF signals definitely have some health issues, but in general, I think it's widely accepted, and I certainly strongly believe that they don't cause cancer. I mean, some people talk about cell phones causing cancer. I just don't buy it. I mean, I think it's silly, frankly. But, okay, don't quote me on that because I'm not a health professional. So the FDA can't come and get mad at me. But I don't believe it. I'm sorry. Okay, so there's no ionizing exposure. There is exposure to RF energy, which can cause eddy currents in your body that can cause unintended stimulation of your central or peripheral nervous system. So basically, if they crank it up too high, your arms might start flopping around. Okay? So, which isn't exactly fun. I've never actually had it happen to me. I mean, I don't think it does anything permanent damage, but they definitely have to avoid that. So they have to measure those things carefully and not have gradients of the coils too high. So there are some issues, okay? It's not perfect, but you don't have ionizing radiation that causes cancer. Now, one of the things that's really nice about MR is it's very flexible. It's basically a software programmable module. There are some issues with the hardware. You have to design coils. By getting the coil closer to the physical tissue that's being measured, you can get a better signal, okay? But a lot of it is just designing of software, designing of signals and algorithms based upon C code and software. So it's pretty much programmable, and we'll describe that, okay? So that makes it very flexible, but it is expensive. So an MR scan typically costs, at least twice what a CT scan costs. Both the infrastructure, I mean, the capital cost of the actual device is higher because you need a large superconducting magnet. And one of the reasons it's expensive is it's slow, which is another disadvantage. So it's not good at capturing very high-speed images. There have been things to speed it up, and maybe people would argue, well, that's not really true that it's slow, but, no, it's slow, okay? It tends to be slower. And it's actually noisy in an acoustic sense. It's like a gigantic speaker. So when you have these gradients, it's like you're putting an input to a gigantic Bose speaker, okay? And it makes a lot of noise. So, that can be uncomfortable for the patient. They can wear a protective headphones to protect their hearing. But in some cases, it's more than just uncomfortable. It also can interfere with the measurements you want to make because the acoustic signal creates auditory stimulus of your auditory central nervous system, and if that's what you're trying to measure in a functional imaging modality, then that's a problem. But MR has a lot of very interesting attributes. One of the most important is that it's a functional imaging modality. CT can be used for functional imaging, but it's very restricted. It's sort of there are things they can do with it, but it's not generally thought of as a functional imaging modality or a molecular imaging modality. And MR is. So you can actually do imaging of a person's brain while they're thinking and see there's shifts in the blood oxygenation level. So the amount of oxygen in the glucose can shift the paramagnetic susceptibility of the cells, so that small shift causes the MR response to shift a little bit, and you can actually detect that, so you can actually see which parts of the brain are thinking. And that's a powerful technique used in neuroscience and psychology, and has some clinical applications too for people who have a particular central nervous system problems. And then there's also things like MR tagging. I'm not a radiologist, and MR has certain deficiencies in certain types of tissue and certain advantages in others. I think, for instance, bone, it's not that good, but some kinds of brain tissue, neuroimaging, people tend to like it. But neuroimaging is done a lot with CT also. Now, mostly what I want to focus in on is the algorithms for doing the reconstruction, which are quite different than they are with CT. Okay, so now my explanation here is fraught with oversimplification. Okay, so I'm really trying to focus on the signal processing. So the physics here is horribly oversimplified. Okay, but I just want to kind of get some kind of baseline model in place so we can talk about the signal processing and understand how that's done. Okay, so what happens is that the concept in MR is that there's precession of atoms that have a magnetic dipole around the axis of the magnetic field. Okay, so it's like a top is the way it's described. So you know how a top will precess when it's kind of winding down. Well, the same thing happens with atoms. So the frequency of precession depends upon the particular atom. Okay, and it also depends on the intensity of the magnetic field. So typically, imaging with MR is done with hydrogen, although it doesn't have to be. But most MR scanners are designed to image hydrogen, so all the center frequencies and everything are set up for hydrogen. And I should write down every year. I threaten to write down what the frequencies are. So they're it's something like 43 megahertz or something like this. For does anybody know what is the frequency associated with the magnetic with the oscillation frequency of hydrogen at 1.5 Tesla? There's nobody in here who knows that. So there's obviously nobody doing MR research in here. Okay, well, I'll find that number out. It's a standard number. I think it's something like 46 megahertz. So everything has to be designed around 46 megahertz. Maybe someone wants to Google it, if they have their laptop. Okay, anyway, so it precesses around this magnetic field, and the frequency of precession is the gyromagnetic constant, L, times m, the magnetic field. So L here has units of radians per second per Tesla. Okay, so if you take L, you multiply it by the magnetic field in Tesla, it gives you the frequency of precession, and that is a physical property of the fact of it being hydrogen. There are other species which have this magnetic dipole and will precess, but they'll precess at a different frequency, and that's why it has to be designed for that particular species. Okay, so now the trick is then to get this precession. What will end up happening is as this thing's precessing, well, first of all, you can pump energy into the system with an RF signal and actually get this thing to oscillate with the RF signal, as long as the RF signal is at the center frequency of the precession. And then the other thing is, once you take the RF signal away, this precessing dipole will radiate RF energy also, until finally all the energy is lost, right? It's like the top eventually falls over. So you can actually sense the precession frequency, okay? So now the trick is going to be, we're going to use this and use Fourier transform techniques to reconstruct a 3D cross-section of the tissue in a human. And we'll talk about this next time in more detail. All right, thanks. Bye.